Hey, good morning. This is David. Appreciate you joining us today. Please let us know if we can help you with any of your HVACR skills training needs. We have 1, 2, and 3-day courses here at our live equipment lab in Garner, North Carolina. And of course, several things in here are mobile and ready to take to a live hands-on training event for your team at your location, wherever you may be. So give us a call or check us out at HVACRskills.com. Want to spend just a few minutes this morning talking about what some folks call a ghost voltage. And just in time for Halloween, we're going to have a quick video here about a ghost in the machine. It is due to something called a Snubber circuit. So a student of ours ran across this during a lab activity yesterday, and before I unwire and tear down some of these lab exercises and reset for the next class, I thought I would take this moment here to demonstrate what he ran into and how it can lead to the misdiagnosis of certain components and controls. First of all, we've got a functioning heat pump wired here on the table, and the only difference between a real heat pump and what we have on the tabletop here is we've simply got light bulbs instead of the major motor loads. So I'm going to set this thermostat for heating operation, and I'm going to call for heat. And of course, we brought on our compressor and our outdoor fan bulb, and back in the background there is our indoor blower. So we're operating in first stage heat now, with this simulation. I'm going to move this where we can take a look now at some of the voltage measurements in our low voltage circuit. Whenever we have an active call for heat on a heat pump, we're going to have a compressor signal coming from that thermostat on the Y or yellow wire or Y terminal coming here to this defrost control, which would be housed in the outdoor unit. So this defrost control gets the yellow or Y signal from the thermostat, and if in fact our time delay has expired and our pressure switches are closed and there's no other faults within the control, then that board will allow the signal to continue on to the compressor contactor coil, and that's what gives us our compressor and outdoor fan operation. So on an active call, whenever we want to establish if the thermostat is calling, we're going to use 1 meter lead and always reference our common, and then we're going to see what is calling on the other terminals. So for instance, on this heat pump, common and B is energized because this particular unit energizes the reversing valve in the heating mode. So I have 24 volts or a nominal 24 volts from common to B. This signal will always be there as long as the thermostat mode selection is in the heat position, just as if a system that energizes a reversing valve in the cooling mode is always going to have O as a live output whenever the system is set to cool. It doesn't have to be calling for operation. I don't know if you have walked by an outdoor unit before and just heard a buzzing noise with a heat pump. More than likely that is the reversing valve coil energized and ready and waiting for the system to start so that the compressor can create the necessary pressure differential to shift that reversing valve. So right now we've got a common and Y signal around 27 volts here, and we've got an active call for first stage heating. I'm going to change the set point here on this thermostat, cutting the system off, and now when I check between common and Y, I essentially have 0 volts. Understand, whenever I'm checking voltage with a voltmeter, with a digital voltmeter, it's very sensitive. It can pick up some transient signals, and sometimes I'm checking for 24 volts and I may see 7.1 or 11.7 or whatever the case may be. Just understand what you have to make this thing work. Any low voltage control that calls for 24 volts has got to have between 19 and 30 volts. Don't spend your time chasing a partial voltage. If it is not in the range of 19 to 30 volts, at that point, whatever the meter is displaying, treat it like it's 0 keep working your way back in the circuit to find where that broken wire or that open signal is. But if it's less than the minimum range that you need, again 19 volts minimum here, anything less than that I'm going to treat it like it's zero and move on with the diagnostic process from there. So we have no more voltage on common and Y, and of course the unit is off. But what happens is sometimes technicians will actually unplug the wires. So I'm going to unplug common and Y, and they want to check the voltage in the wires themselves. And if you notice now, my meter has gone back to around 28 volts. This thermostat is not calling for operation. We've got 67 degree room temperature, a 64 degree set point. We are not calling for any heating operation. But once again, on common and Y, the wires themselves, I am reading a 28 volt signal here. These very same wires, when I plug back onto the control, this is where the ghost part comes in, because when I plug them onto control and now check the very same wire points, I have gone back to 0 volts because the signal that we thought we saw really is not there. This particular voltage is due to something called a Snubber circuit, and honestly the subtitle of this video should be always leave the wires connected to the load device when you're measuring the voltage. If I simply unplug the wires and check on the wire itself, and I can reference common here on the board, that yellow wire is hot. That yellow wire is giving me 28 volts. But when I connect this back to the control that it's supposed to be powering and recheck the voltage, once again we're at 0 volts. Always check your voltage with the wires attached to the load that you are testing. The reason that this is happening is due to something called a Snubber circuit within this electronic thermostat. You'll find this also with some various output circuits to reversing valves and contactors from defrost controls. You'll find this in certain zoning controls. But in any case, when I disconnect the wire from the load, I'm going to see an apparent voltage because of a feed through a resistor and a capacitor circuit within this thermostat that is actually in parallel with the control contacts. So on the left-hand side of this little diagram here, everything flowing from left to right, so to speak, we have our thermostat input signal being hot, 24 volts, our R terminal, and the output for the compressor is my Y terminal. And inside this thermostat, you've got a normally open set of control contacts that will close anytime I have a command for this first stage compressor operation. When I disconnect a wire, I'm seeing a back feed through this resistor circuit that's crossing over those normally open contacts, and it gives me an apparent voltage on those wires when those wires are disconnected. When I connect them to the load, the resistor and capacitor are not really flowing voltage, so to speak, so you really don't have any voltage at the load, and that's why it goes to 0 whenever you connect it back to the load. But when I disconnect the wires and have them just dangling loose and I check the voltage at the end of those wires, I will always have an apparent 24 volt signal because of this Snubber circuit. This acts as a filter to dampen, some of the potential arcing that could happen across these contacts. And again, many of your electronic controls have a Snubber circuit. So again, the moral of the story is to always leave the wires connected when we make voltage measurements, whether we're confirming reversing valve signals, compressor contactor signals, or anything along those lines. Always leave these wires attached to the device that we are testing. and that is the ghost voltage caused by a snubber circuit. If you want to take a look at HVACRskills.com, I've got a diagram of this and a quick write-up in our resources page, and by all means, if we can help you with anything else related to HVAC skills training and testing, please let us know. Be glad to hear from you. Hope you have a great day.